It's always nice to be in New York.
And Zurich.
And Zurich. Both of them are fantastic cities. Yeah, so this talk is about supervised learning. So this is, we have data. We will have data that are, pairs of xi, yi, labels and feature vectors. And IID from some common distribution and want to learn a function f that enables us to predict new labels given a new feature vector. And the objective is to minimize some prediction error, some test error that is the expectation of the population distribution of the loss. Okay. And okay, if you take a class or if you give a class in this topic, you'll probably teach these three kind of main pillars of this theory, of machine learning theory. The first one, you'll teach students that you probably want to try to minimize the empirical risk, that is the average over the sample of the loss. And the reason you want to do this is that, well, in reality, you want to predict the expectation of the loss. But, you might hope that there is some kind of uniform convergence phenomenon taking on. So the empirical risk is uniformly close over to the population risk for all predictors in a certain function class that I'll call script f. And then you ask yourself, okay, how do you want to do this? How do you want to minimize the empirical risk in practice? Well, the main path is to choose a function class and a loss function so that the empirical risk minimization problem is convex. Okay, and okay, here I sneaked in this of course, this important thing that I don't minimize over all function, but only over a certain function class. And the reason is pretty simple, is that if I minimize over every function, I end up with trivial examples like this one, in which I can fit perfectly the data, but not predict outside the data point, not be able to predict outside the data point. Okay, so this is all nice and beautiful. It has new beautiful math in it. Unfortunately, since about 2010, for a bunch of application, it's fair to say that practitioners have pretty much ignored all of this beautiful math. And okay, just to give an example, the elephant in the room is, of course, neural networks. If you don't know what they are, an example is a multi-layer neural network. Here, the parameter space, the parameter is a set of L matrices. This is for an L-layer networks. The dimensions of these matrices are chosen such that they can concatenate from W1 to WL. And the function class parameterized by these matrices is simply the concatenation of product by such a matrix and application of a nonlinear activation function. And here matrices, of course, acts on vector by left multiplication, and sigma is a nonlinear function. These are two standard examples, and the function, a scalar function, acts to a vector by component-wise action. Okay, so let me go over all the three kind of pillars of machine learning theory that I described before, and argue that they don't hold, or they don't hold in any obvious way anymore. The first one to go is, of course, convex optimization. Even if you take square objective, or pretty much any objective, this optimization problem is highly non-convex in the parameter W's. The second to go is uniform convergence, and this is a very well-known example in a paper by a group at Google Brain, in which they show that if you fit a standard data set using a state-of-the-art neural network on the true labels, the training error, so the empirical risk, could go to zero pretty quickly. And not only that, and of course the test error is not zero. The test error for this example is here. This was the inception network. And even if you test it on purely, run it on purely random labels, the test error goes down even if slowly, but goes down and reaches 0. Okay, and what this means, it means that somehow your network is rich enough to interpolate the data points, so to achieve test error, train error equal to 0. So we are seemingly very far from the uniform convergence regime in the sense that the training error is 0, and of course this is very different from the test error that is stays different from 0. It's small, but is non-zero. And even if you corrupt the data, you can make the test error pretty large. So here you replace part of the labels by random labels. So the test error degrades gracefully, but the training error stays 0 all the way. And this is another kind of experiment to demonstrate the same point. Here, the test error and training error are plotted as a function of the number of parameters in a 2 layers neural networks. And you see that when the numbers of parameter crosses a threshold, the train error reaches 0. So this is the point at which you have as many parameters as constraints that come in from the train set. And despite this, the minimum test error is achieved at very large overparametrization when you are well in the regime in which the train error is very small. So this is the uniform convergence regime that we normally think about, and this is the regime in which is most convenient to operate this network. So this is from a paper from Misha Belkin and co-authors. Finally, you might think, okay, this is all fine, but at least empirical risk minimization stays on, because after all, we are minimizing the empirical risk with these things. Not completely true, because in practice, what you do is run gradient descent or stochastic gradient descent, and in this problem there is a large number of local minima. They are highly non-convex. In fact, a large number of global optimal with train error near 0. They are largely non-convex, and therefore what this algorithm converges to really depends on a lot of factors. It's not just the optimization problem or the cost function. It also depends on the initialization, on step size, on all sorts of minute details. Okay, so saying I'm minimizing a certain cost is not really the crucial part. Everything is crucial, even how big is the step size, etc. Okay, so in this talk, I want to try to describe some simple model in which some pieces of this puzzle can be understood theoretically, mathematically. I will describe the setting, and then I'll focus on 2 examples. One is ridge regression, basically, and the other is max margin classification, and then describe some current research directions. And this is based on work with actually 2 groups of wonderful students, Berus Gorbani, Song Mei, and Theodor Misiakiewicz for the ridge regression part, and Feng Ruan, Yongtak Son, and Jun Yan for the classification part. Okay, and of course, I should mention straight ahead that this is, of course, we are not the only one that tried to understand this thing. There is, a huge number of papers appeared over the last 2 years. In particular, Misha Belkin has been very influential in pushing this kind of, the study of simple model to understand this problem. And here I only list a few papers in 2019, and there is many more in 2020. And the difference between our work and this work is that we try to get exact asymptotics in models that, okay, they are simple, but they are somehow directly connected to neural networks, and more specifically, they are random feature models. Okay, so let me start with the setting. So again, we have IID data pairs. We'll assume a very simple distribution for the data. The feature vector will be uniform on the sphere in d dimension of radius square root of d, such that each coordinate of the feature vector is a variance 1, or normal 0i. And okay, we'll focus on the high-dimensional regime because it's not hard to understand that this phenomenon in which you get zero training error, and so you interpolate the data and good test error, is much easier or much more natural in high dimension than in low dimension. And these are the feature vector. The response variable are, in the regression case, they are a function of the feature vector plus noise. In the classification problem, we will have a function, G star, that is a function of a linear projection, one-dimensional projection of the feature vector, and the label probabilities is given by this. So I hope this is clear. I cannot see the audience nodding, but please interrupt me if the model is unclear. So this was the distribution of the data. The model, the statistical model that we look at is the random feature models. This is a class of function parameterized by this coefficient AI, in which I take a set of neurons. So I pass my data to a set of neurons, so a set of activation function. I have capital N neurons, and then I combine this with coefficient AI. And here the first, so this is a 2 layers fully connected network, but important I think that I train only the second layer. So I train only the AI. And the W are fixed, and I'll take them random, okay? So each of these WI is uniform on the unit sphere. And this dates back, well, in some sense to Neal, but was really, this type of model was really very much developed by Rahimi and became popular after Rahimi like 2008 paper. Okay, so this was the data and the model, and I'll train this model in 2 ways. For regression, I'll use ridge regression, and for classification, I'll use max margin classification. And if you want formulae, these are the formula for ridge regression and max margin. They are different in the sense that ridge regression is linear in the data, max margin classification is non-linear in the data. You don't solve a quadratic problem in the AI. This is a quadratic problem in the AI because the function class is linear in A. But they are similar geometrically in the sense that what matters here is the 2 norm of A, of course. Okay, so why I'm interested this random feature class is a neural network in which I train only the first layer, but okay, why that might be interesting? Well, there is a connection, there is the, relatively direct with actual neural networks to the so-called lazy regime. So this is terminology of Shizabak. And what is the picture that I draw here? Here is my mental picture of what is the space of empirical risk minimizers with value 0. So this is the set of theta such that f of xi, I'm thinking of regression here, is equal yi for each I. Okay, and if p, so this is RP, a picture of RP in P very large, and if P is much bigger than N, you expect this set to be a high-dimensional manifold. So this is this high-dimensional manifold. So then you start training a some initialization theta 0, and you run gradient descent. You'll converge at some point that is a perfect interpolator that is close to the initialization. Okay, so this is a high-dimensional manifold, and why you can converge to a point close to initialization? Because I expect that there exists a solution of this equation, this set of equation, close to every point. And the reason is, well, the heuristic reason is that I can perhaps try to expand this, Taylor expand this around the initialization. And therefore, I can, solve this linear, if this gradient, so this is the gradient of f with respect to theta, if this gradient applied on the point of the test point xi is full rank, and if higher order terms are non-zero, higher order terms are negligible, I can hope to solve this just by inverting this part. So in the neighborhood of the initialization, in many cases I can neglect this part, the zeroth order part, and if I call this coefficient a, this difference of parameter a, I can parameterize, think of my function as parameterized by the difference from the initialization and taking the form A transpose times a feature map of x at theta 0. And so this is a set of linear coefficient, and this is a random feature map. Okay. So in the neighborhood of any initialization, any model, any nonlinear model looks, like a random feature model, possibly for a very complicated random feature map. And since I can find a point, a solution to this empirical risk minimization problem close to the initialization, it's perhaps fine to look at this linearization across the initialization, around the initialization. So this explains why this random feature map is interesting. While should I look at ridge regression? Well, because locally the landscape around the initialization theta 0, locally the landscape will look quadratic, again, because the function, at least this is in ridge regression, my function is linear in the parameter, and therefore if you have a landscape that is quadratic, gradient descent converges to the point theta hat that is closest to the initialization in L2 sense. And so this is just rewriting that in formula. If you have a gradient descent and you have an empirical risk that is, a risk for a square loss, so x quadratic in A, then in the overparametrized regime, in which there is many, indeed in any regime, many solutions to the risk minimization problem, the limit of gradient descent as time goes to infinity coincide with the ridgeless limit of ridge regression. And okay, a similar motivation exists for max margin classification. If you do gradient descent with respect to the empirical logistic loss, and here again the function class is linear in the A's, then again in the overparametrized regime there is many empirical risk minimizer. I mean, the empirical risk minimizer are at infinity in a sense. But if you run gradient descent, what matters is really not the coefficient A in this case, but the coefficient A normalized by its norm, so the direction of the coefficient A. The coefficient A will diverge, but its normalized form will converge to a vector that is the max margin classifier. So in a sense, by studying ridge regression and max margin classification, we are studying the asymptotic limit of gradient descent in the overparametrized regime. Okay, so results. So it's interesting to start by considering the infinite width limit. So here in this problem, we have three parameters somehow: the dimension of the input dimension, the number of samples n, so these are the usual parameters that are most used with, but there is also another parameter that is the number of neurons. So this is the input dimension, and this is the dimension of the parameter space. So infinite width limit I focus on is the limit of infinite number of neurons. Okay, so a way to look at it is to look at the connection with kernels. Again, ridge regression in this problem, I can look at this as a minimization over a space of functions where I minimize over all functions and then I penalize function by a RKHS norm. So instead of minimizing this, I minimize the RKHS norm. And okay, this is a special RKHS norm because it's the norm for the empirical average, the empirical outer product of the sigma. So it's a finite rank kernel. So it ends up being a finite dimensional optimization problem. Okay, but if you look at this way, then it's natural to think that as the number of neurons goes to infinity, this kernel converges to its expectation. And in fact, it does in many different senses, and this was studied in many papers. So many papers looked at this connection. And so what happens now when you take n to infinity? So you are doing a regression with respect to this thing, and let me discuss for a moment what happens in the regime in which the number of sample is proportional to the dimension. So now we are left with two parameters: the number of samples and the dimension. And since our distribution over the neuron, the first layer weight is isotropic, so this was uniform on the unit sphere, the kernel will be a function, will be rotational invariant, and since here we are living on the sphere, will be a function of the angle between the two vector x1 and x2. So the kernel evaluated these 2 points is a function h of x1 dot x2. And in fact, there is this divided by t because it's a function really of the correlation between W transpose x1 and W transpose x2. And the correlation between these two vectors is that quantity. Okay. So here is a very simple observation or result about this type of kernel, and I think the first one who noticed this, who showed this, is El Karoui, 2010, and the observation is the following: is that, well, if x1 and x2 or xi and xj are two random vectors, this quantity is of order 1 over square root of d, right? So it's very small. So it makes sense to Taylor expand h around 0. So if I look at the kernel matrix, that is the empirical kernel matrix, the matrix with these entries, I get that Kij is h0 plus h prime of 0, xi, xj divided by d, plus higher order terms. Okay, and okay, so if I think of it as a matrix, this is a constant times 1, 1 transpose, so not very interesting, is the constant matrix. This is interesting, this is another constant, h prime of 0 over d, times x transpose x. And then all other terms, well, this, if you subtract the constant, each of these entries is of order 1 over d. So this error term is in operator norm is of order 1 over d, and then is an n by n matrix, so you get a square root of n. Right? So this term is much smaller than 1. So the operator norm of this term is much smaller than 1. So the kernel is approximately linear. And so this is saying that basically what you are doing in high dimension with this rotational invariant function, you are doing linear regression. The only thing that you are fitting really are linear functions. So this is what happens in the proportional regime. The kernel is approximated by the kernel of, the linear kernel. And okay, so what happens beyond this proportional regime? There is a natural, very natural and elegant generalization of this. If you have some very mild regularity condition, the following happens: if the sample size is between d to the L and d to the L plus 1. We saw before, if the sample size is linear, basically you're doing linear regression. If it is between d to the L plus 1, then for any positive regularization value, the risk of kernel regression is the projection of your target function, f star is my target function, over polynomials of degree L plus 1 or bigger, plus a small order term. Okay, and no kernel method can do better than this. So basically, kernel regression is basically doing approximating functions, projecting functions onto polynomial. One important, interesting fact about this result is that this is optimal, and it holds for any positive regularization. So in particular, it tells you that optimal regression among kernel method is achieved in this setting at lambda equals 0. So lambda equals 0 means no regularization. So it means that I'm interpolating the data. So I'm interpolating the data and still I'm achieving optimal prediction in this kernel world. And there is this interesting, star case phenomenon that when log n over log d crosses an integer, you fit one more layers of polynomials. Okay, so this was the picture of in the very wide regime in which I can basically approximate these neural networks by kind of fuller rank kernels in L2. What happens when instead I look at a finite number of features, so finite number of neurons, and now from now on I focus on this proportional asymptotic in which these three parameters are proportional to each other. And okay, my target function will be a combination of a linear component and a nonlinear component, and it's important to separate these two because, as we saw before, we expect to be able to fit only the linear part. Okay, so I call f1 the intensity, the size of the linear part, and f star the size of the nonlinear part, and psi1 and psi2 the asymptotic ratio of, so psi1 is number of neuron and psi2 is the sample size. Okay, so this is a model, and for this model we can compute the asymptotics of the risk, and the theorem goes like this. Take the activation function. All that matters about the activation function is the decomposition into the linear and the nonlinear part. And this is the decomposition, the orthogonal decomposition is in L2 of the standard Gaussian space. Okay, so he has to satisfy this constraint. Right? Then for any lambda, we obtain an asymptotic value for the risk that is given, that is explicitly given. So I should emphasize that the variance term was computed in this earlier paper. And this is explicitly given by a function of psi1, psi2, your two aspect ratio, the regularization parameter, and zeta, that is the form factor of the activation function. And this is a bias component. This is proportional to f1, and this is a variance component. And notice that the nonlinear part of the target function only enters as an additive term here and as an additive term in the noise. And what this means, it means basically that everything that is not a linear function acts as noise for my method. Basically, it looks to me as if it was noise. This is as if I had a function in one dimension and there's a very high frequency part and a very low frequency part, and then I sample at 100 points in the interval 0, 1. If the frequency part, high frequency part has frequencies that is much bigger than 100, it will look like noise. Cosine of 1000 theta looks noise sampled at 100 random points. Okay, so I said that I have explicit formula for variance and bias, and these are the explicit formulas. If you are into random matrix theory, you recognize, so you have to solve these two equations that are fourth order equations, and then compute this product, and then substitute into these polynomials, and then you would get your variance. So it looks complicated, but it's very simple. And if you are in the random matrix theory, you recognize that these are really fixed point equation for Stieltjes transforms of random matrix spectral distributions. And the math that is behind this is math, random matrix for kernel inner product random matrices, and we have tools. Not a lot of tools, but some tools to do with it, and these are a few papers starting with Chung and Singer. Okay, so what do these formulae mean? Really, actually, despite they might look complicated, they have a very simple interpretation, and the interpretation is the following. Think of my function class. I want to write this as A transpose times U. So I'm a linear function in some feature vector U, and U is the output of the second layer, the layers of hidden neurons. So UI is sigma of WI transpose times X. Okay, so remember now that I decompose sigma, and okay, let me remind you also that my target is Y is beta transpose times X, and let me forget about the noise and the nonlinear part. So you might hope, since the target is linear, you might hope that what matters only is second order statistics between the feature vectors, the output of the hidden neurons and the target. Okay, so one way to get second order statistics is to decompose the activation function into its linear. So let me forget about the constant part and this nonlinear part. Well, I remind you that these are uncorrelated in the Gaussian space. And therefore, UI will be sigma 1 of WI transpose times X plus some coefficient sigma star times ZI, and the coefficient sigma star is just the norm of sigma in L. And therefore, this guy, ZI, is standardized as it is uncorrelated with Y, and is uncorrelated with all of these. Okay, because this object is Gaussian. So if I do this replacement of the UI, if I write the UI in this one, I get this UI that are uncorrelated with all the rest. Okay, so this leads you to the suspicion that perhaps you can replace your original model by a model in which the ZI are really independent of all the rest. So here they are uncorrelated. I can replace it by something that is uncorrelated. So in this model, the U tilde I call this is what replaced the UI, are Gaussian, and they are correlated with the axis, and they are correlated as prescribed by this. Okay? So what this really theorem, with the complicated formula says, is that in this proportional asymptotic, these two models are equivalent. So the nonlinear feature models, the one that we started with, and the noisy linear feature model, the one with the random independent ZI, are really asymptotically equivalent in the sense of having the same risk. Okay, so this is a conceptual way down. The noisy linear feature models is not a piece of cake. The formulae are complicated, but it's a Gaussian model. So we have ways to deal with it. Okay, so if you plot the curves that are predicted by this formula, you get first of all they match very well with simulations with random feature model, and then you get this scenario. So this is black lines are prediction and points are just theory, and you get very good match, and you get this typical double descent phenomenon in the number of parameters over number of samples, where you have a peak at the interpolation threshold. This is for zero regularization. This is for positive regularization. And then the risk decreases again above the interpolation threshold. And the really interesting point here is that the minimum risk is achieved at infinite overparametrization. So in the infinite, in the very wide regime. I want to spend perhaps a couple of minutes just pulling out a couple of insights from this theory. This is something that I already said. These are again a bunch of these curves for various values of the sample size. Psi2 is basically the ratio of sample size to dimension, and the optimum is always obtained at infinite overparametrization. This is something that people, when they hear about this double descent phenomenon, will always ask you about, and here it's clear. If you regularize your model, the double descent phenomenon disappears. Here I'm adding a ridge regularization, and at zero regularization I get this peak, but if I take the lower envelope of this curve, I see no peak whatsoever. And one interesting thing is that the optimum is at infinite overparametrization, and as you see in this picture, in some cases is achieved by lambda equals 0. Okay, despite the whole curve is not optimal, this point is optimal. And this is indeed the case. There is an interesting phase transition if lambda is, if the SNR is high enough. And this is the regime in which you would think that many neural network applications live, high SNR regime, then the optimum regularization is 0. We know that regularization should increase with the noise, but here up to a certain noise level is strictly 0. Okay, and the reason why you get 0 regularization is optimal is that actually the nonlinearity produces some regularization effect. And this is most easily seen in the wide limit. Okay, perhaps I skip this. Here what I'm plotting is a bias and variance from my formula in the very wide limit as a function of the regularization parameter and zeta2. Zeta2, I remind you, is the ratio of the nonlinear part, the linear part divided by nonlinear part square. Okay, so you see that increasing the regularization has the same effect as decreasing zeta, so adding a nonlinear part to the activation function. Okay. And in fact, if you look at the prediction of our formula, you get that the real, the bias and the risk depends on lambda and sample size only through this combination. So even at 0 regularization, you get some non-residual regularization that is of this form. Right? So this also appears in other papers. For instance, in the case of regression, similar phenomenon was pointed out in a paper by Kobach and co-authors. But here we show it in a real random feature model. Okay, so this is the story more or less for ridge regularization. What happens for max margin? Okay, remind you the model here, I take the truth that is, basically linear. So there is a function G star and my labels are, the probability is G star of beta transpose times Xi. And I look at a prediction error. Here will not be the square error, but the classification error. Okay, so max margin classification is solving this problem. And of course, this is a more difficult problem to understand than the ridge regression. And the reason is that, okay, the fitting procedure is not linear in the Y's and is not linear. So it's given by this convex optimization problem, so it's fairly implicit. So you cannot express it as a random matrix theory problem, a problem about eigenvector and eigenvalue of a random matrix. And now your matrix is complicated because this is your design matrix, because the feature vectors after first layer have correlated entries and they are non-Gaussian. Okay, so we cannot really analyze this at the moment, but what we'll do is that we'll pretend that the same that happens in the ridge regression problem and that we proved in the random ridge regression problem is also true here. Namely, we look at max margin classification in this proportional asymptotic, and we'll pretend or we conjecture that the nonlinear feature model and the noisy linear feature models which is a Gaussian model are asymptotically equivalent. And the same conjecture appeared independently in a work by Gold et al. With very different kind of motivation, but they had a similar conjecture. Okay, so because of that, we are led to analyze the problem for general Gaussian feature. Max margin classification in this setting where now the features are Gaussian with a general covariance, And the assumption of this covariance is that on this problem is that, of course, the aspect ratio converges to a limit. The eigenvalues of this covariance are bounded below and above. And the crucial role is played now, the geometry is encapsulated by the following. You have two parameters here, right? You have sigma and beta 0. And you have to tell me something about what is the geometry of sigma and beta 0. And the way we do it is the following. Look at the di, this is the eigenvector, and look basically of theta 0 in the basis in which sigma is diagonal. Okay, so the component, rescaled in, here we rescale in this way, but that's not really important. But the component of theta 0 in the basis in which sigma is diagonal are called wi. Now we have two vectors, w1, wp. Here I'm calling p the dimension, I think, or n, capital N the dimension, and then lambda 1, lambda n. And what I'm assuming is that if I look at the rows of this matrix, and by two metrics, the empirical distribution of the laws has a limit, and the limit is a weak limit as L goes to infinity. It's actually a W2 limit. Okay, so under these assumptions, again, we can give an asymptotic formula for the prediction error and the margin of the problem that is explicit. I will not go over it in detail, but it works for any mu, so for any geometry of your problem. The key tool here, the tool that we use is Gordon, since we reduce ourselves to a case in which covariates are Gaussian, to Gordon inequality. And so this was very much popularized by CB and co-authors for this kind of problems, or developed by them. And there is a challenge here that is often overlooked, is that you have to prove that Gordon's problem has a unique solution asymptotically, and this is, in this case, a bit tricky because you have all of this complicated geometry mu. But okay, we find a way to do this that I think it's interesting. So if you are into this kind of technical thing, I recommend you to read it. Now we can take this big theorem and apply to our noisy linear feature models that gives you and me a specific structure of sigma that is a constant times WW transpose, where this is the matrix of first layer weights plus identity. So now we take this one, we prove that the assumption of the theorem is satisfied, and we evaluate the formula, and we get some formula for the error and the margin. And okay, so I want to say just a couple of things. The first thing is that we recover basically the same phenomenology that we saw in the case of ridge regression. So, but the details of these are quite different, of course. As the overparametrization increases, there is a phase transition in which data becomes, the train error becomes 0. So what does it mean that the train error becomes 0? It means that the data becomes linearly separable. So it becomes that the margin develops. Okay, so at a certain value of the ratio n over n, so I'm embedding small n points in capital N dimension. Okay, and I'm embedding them to this map. And at certain points, this becomes separable. And okay, this is a phase transition. In the simpler case for random points with random label, the separability phase transition dates back to Cover in the 60s, 60 something, and the value was 2 or 1/2, 2. And for here there are two complications, that the geometry of the data is more complicated, and the value of the labels is non-random. For non-random label and linear feature, this threshold was computed by Candace and Sur a couple of years ago, and here we compute the threshold and all evolution of the margin. So the margin increases as you embed in larger and larger dimension, but interestingly, the test error decreases. Okay, And the optimal error is again achieved in the wide limit, in which the number of neurons over number of dimension goes to infinity. Now, the wide limit has a nice interpretation. So the limit here is a nice interpretation that I want to describe. And it turns out to correspond to a soft margin classifier. So my data, again, are non-separable. So max margin classification in the linear feature way without this nonlinear featureization map doesn't make any sense. There is no margin. Okay, so something that you can do. Okay, I don't know if anybody does this. Probably they do, but I discovered this method by doing this calculation. Is the following: I add some slack variable here si, and I multiply by some coefficient sigma star. Sigma star will correspond to the nonlinear part of sigma. And now I minimize this standard max margin classification set s equals 0. And now instead I minimize this over both A and S, and I'll impose this constraint. We have two constraints both on A and S. So this is a method. I don't know if it makes sense. I don't know if anybody studied it before. Probably they did. And this is what I'm doing instead. I'm doing something seemingly very different. I'm taking my feature vectors, I'm passing through a random neural network, and then I'm embedding through a random map constructed in this strange way in high dimension, and then I'm doing max margin. I'm choosing the dimension very large so that they separate well, and I'm doing max margin. And the theorem is that the two things are basically is an interpretation of the theorem that I gave before, is that the two things are equivalent in the wide limit. Okay, so I find this kind of interesting. So both in the kind of ridge regression, we had this interpretation that what you are doing by embedding in 9 dimension was adding a ridge penalty, basically. Here we have this interpretation that what you are doing is moving from max margin classification to soft margin. And geometrically, really the picture that I have in mind is that you have this point that you are trying to classify. And what you come up with is something like this. It's something that is almost a linear separator, but unfortunately your data are not linearly separable, so you do something like this. Okay, I guess. So you really separate them, so you achieve 0 training error. Your thing performs like a linear separator, and you pay something that is a combination in your optimization problem. You try to combine penalize a combination of the margin and of all this length of these stretchy parts here. Okay, I have perhaps 5 minutes. I want to discuss some conclusion. So again, a big part in a standard machine learning theory class is the point that you make that you have to be very careful about trading between model complexity and sample size. You have to tailor your function class or your norm that you are penalizing things with to be the right amount so you don't overfit. Here, basically, things in these models that I describe and empirically in neural network, things work quite well without paying much attention to regularization. There is some implicit regularization that comes up because of the algorithm, because of the mean norm, but I'm not careful at all about what lambda I'm picking. I'm just setting it to 0. And unfortunately, now we understand it rather well in these simple models, but okay, there is of course much more to do. So one nice thing with these simple models is that you can do calculations. So you can now set up a small industry and look at all sorts of other settings. And these are three that we are currently, so soon papers will appear. One is here I looked at the random feature model. It's of course interesting to look at the real neural tangent model. I looked at very simple data distribution that are completely anisotropic. It's important to understand what is the effect of an anisotropic data distribution. And finally, here I'm in this setting in which I'm training and testing the data. First of all, I'm training and testing the data on the same data distribution. This is probably not the case in practice. And then, so this is one interesting direction. Another interesting direction is, well, one thing that you notice in practice is that the model that you get in neural network depends a lot on the initialization. And what the initialization is in this case, well, it's the matrix W. If you remember where this comes from, it comes from this idea that my linear model is really a linear approximation of the data of my nonlinear model around a random initialization. Okay, and okay, therefore, changing the initialization means changing the featureization map. Of course, I don't want to pretend that this linear model is accurate in any detailed description of a neural network. I want just to pretend that it's capturing some of the phenomena. So one of the phenomena is that changing initialization will correspond to changing the random feature map. So it makes sense to try to study the effect of changing the feature map on my predictor, and this is one setting in which we can do this precisely. I'll just give you a teaser. One way to study this is you look at, again, this is the function that we are looking at, and this is the mean norm interpolant. Okay, here I should have put a square and perhaps a parenthesis. And I'll define the sensitivity for two matrices W1 and W2 as the L2 change in my prediction model when I change my feature map from W1 to W2. So this is supposed to model, how much my model changes when I change initialization. And this we can compute it in this random feature model. We can compute it exactly, and interestingly, is extremely large. Namely, if you normalize the initialization by the risk, so the risk is the L2 distance from the truth. So it cannot change too much because we know that typically this model has a certain risk. So there is the true function, and then there is two models. This is in L2 space, F1, F2, that you obtain by fitting with two different feature maps. These have the same scalar product with F star, but given that they are the same scalar product with F star, these are as far as possible. So if you change the initialization, basically you change randomly your function. Okay, that's all I guess. Thank you.
Thanks for the great talk. It's hard to clap on Zoom, but there's lots of virtual.
No problem.